All right, everybody, welcome to Chapter 3. This is where we're going to live the rest of the trimester. It is. Chapter 3 has 9 sections in it. It's massive. Basically, the entire chapter is focused on just calculating derivatives. So the beginning of the chapter, we're going to talk about, like today.
Can I go grab my notebook real quick?
Real quick, yeah. So today we're going to talk about what is a derivative, and so how it's related to some calculations you guys have done before. Then we're going to move into differentiability, which is how do you know if a function has a derivative or not. And then we're going to talk about the whole rest of the chapter, basically techniques of taking a derivative for whatever kind of function you might have. So there's a whole section on derivatives of trig functions. There's a whole section on derivatives of logs and exponentials. There's a whole section on doing derivatives of rational functions. So we kind of break it up into all these little chunks, but there are lots of different functions out there, and each one of them we're going to hit and talk about until at the end of this chapter, I can give you any function in the world, and you can take the derivative of it and explain what that means and use it. So there's a lot to do, so it's kind of long. All right, but today we're just going to kind of like lay the groundwork as far as, like I said, what is a derivative. So 3.1 is just simply called derivative of a function. Okay, so the definition of a derivative is going to look kind of familiar because you've actually done it before. The notation that we use for a derivative looks like that. Actually, there's more than one, but this is the first one we'll look at. This is the Newtonian way of writing it. Okay, so Newton studied calculus, and many people believe that he invented calculus or discovered calculus or whatever. So when he was talking about derivatives, he used this little notation. It's f prime of x was his derivative, and here's how he defined it. It is the limit as h goes to 0 of f of x plus h minus f of x all divided by h. What is that? Instantaneous rate of change. Guess what? That's a derivative. It's just another name for a derivative. You've already done it before.
We better stop now.
I know, it's crazy time, right? So derivative is the instantaneous rate of change. Okay, and we're going to look at two different ways of viewing a derivative, I guess. There's a derivative at a point, which is what you guys have done before, and then there's a derivative function. Okay? This right here is actually a derivative function. Now I'm going to change this just slightly to make it a derivative at a point. What's the only difference between those two things? Yeah, instead of x, it's a, right? And so x is a variable. It stays a variable once you're done. A is some number that I'm plugging into it, okay? So this is going to be the derivative at a point x equals a. So it's really doing, the calculation really is the same thing. It's just instead of having an x in there, you're immediately plugging in a number for x and doing it that way instead, okay? And we've pretty much been doing this kind of thing. Derivative at a point. But let's see if we can do the derivative function too, though. Okay? So let's say f of x is equal to 2x squared minus 5, and the directions will be something like find f prime of x. So we're going to go to our derivative function. Notice how it doesn't say f prime of some number, it's f prime of x. So we're doing this one up here, the derivative function. Alright, so f prime of x equals the limit as h goes to 0, f of x plus h. So 2x plus h squared minus 5. Okay, so that's the f of x plus h. And then minus f of x. Okay, well, this is f of x, right? So it's just that whole function, 2x squared minus 5, getting subtracted. And then all of that divided by h. And at this point, it's kind of the same game we were playing before. You got to multiply everything out, distribute everything, get all of that numerator as a bunch of terms all added and subtracted up at the top, and then see what cancels out. And we're hoping, again, that that h should cancel with everything on the top so that you have something then that's usable where you can actually come up with the answer. So let's go through that then. So we got limit as h goes to 0. So let's see, if I multiply that all out, so I'm going to have 2, and then that's going to be x squared plus 2xh plus h squared minus 5, and then I'm going to distribute that negative, so minus 2x squared plus 5, all divided by h. And then I got to distribute that too real quick, so let's do that real fast and check to see what we got there then. So 2x squared plus 4xh plus 2h squared. I guess we could just get rid of the minus 5 and the plus 5 at this point, because those will cancel each other out. Okay, anything else in there you guys see that it's going to cancel out? The 2x squareds will be gone. And then once I divide everything by h, let's see what I got. So this h will be gone, and then the square on that h will be gone. So it'll be the limit as h goes to 0 of 4x plus 2h. Everybody follow me there? Did a couple things at once there. And then what is my answer? Because I can plug the 0 in now for h. 4x. Congratulations, you have calculated your first derivative. That is a function. So f prime of x equals 4x. All right, there is a lot of power in what you just did here, because what you have now is a derivative function, which means if I want to find the instantaneous rate of change of this original function, 2x squared minus 5, let's say at 2, what's the answer? 8. If I want to find the instantaneous rate of change of that original function at 4, what's the answer? 16. At 0, 0. So anywhere on that curve I want an instantaneous rate of change. If I'm looking at the tangent line, the slope of the tangent line, anywhere on that particular curve, I can find it now. I don't have to recreate this whole limit as h goes to 0 business for every single one of them. I have a function I can use. I can just plug right into that thing and get my answer every time. Okay? So this chapter, I said we're going to be focusing on calculating derivatives for whatever. We're going to be coming up with these guys. We're going to be coming up with derivative functions that allows us to plug whatever we want into them for that particular function and not have to keep doing this limit thing over and over and over and over again. Okay, so that's how I'm doing that. Okay, so let's try this one more time, just so we're getting used to it. Let's do f of x and we'll do one that we haven't really approached before, but we can probably access here still. F of x equals the square root of x. And let's find f prime of x for this one. Okay, so that definition then tells us f prime of x is going to be the limit as h goes to 0 of f of x plus h, so the square root of x plus h minus f of x all over h. Okay, so when we try and do this now, remember what we're trying to do is we're trying to figure out how we could simplify that numerator so that we can get things to cancel out. Okay, so what do you notice about that? Guys have any techniques of ways that we could simplify that numerator? Give you a hint. It's okay to say no. No, I don't know. No. Square root of x plus h minus square root of x? No, not particularly. So there's an alternate definition of a derivative that we can use, and we're gonna for this one, okay, that might make it a little bit easier. And this is a derivative at a point, so it's f prime of a, but it'll help us with this as well. Whoops. Whoa, sorry about that. Oh, thanks. Okay, so it should look somewhat familiar, like at least it looks similar to the one that we looked at before, but a little bit different. Okay, so instead of using h, we're just using x. So it's the limit as x goes to a. It's still on the top, kind of a change in the y, on the bottom, change in the x, except we're doing the limit as x goes to a. So think about that. If I tried to do this as a substitution limit again to start off with, what would I end up with underneath here? If I substituted a for x right away, it'd be 0 on the bottom again, right? So again, we are looking for some way to simplify this thing as much as we can to kind of eliminate this x minus a. And when it comes to functions like this